In Chapter 7, we will continue our discussions about EMS databases and explore how they support quality analysis. Once completed with this module, you should be able to identify and calculate measures of central tendency, interpret and apply correlation tests to determine causation and correlation with a set of data, identify patterns in statistics and apply formulas to identify and interpret those patterns as significant or correlating. Given a set of data, select the proper displays and ways to communicate the results of analysis of data, distinguish between comparative and non-comparative measurement scales, describe efficient ways of ordering, analyzing, and summarizing qualitative data, and designate, at the end of data analysis, what additional activities are needed to test, confirm, and prove data validity. To illustrate the importance of data and research within EMS, consider this scenario. One of your EMS crews was called to the scene of a 32-year-old male with a rapid heartbeat. It was determined by the EMS crew that the patient was suffering from unstable supraventricular tachycardia and delivered a 100-joule synchronized shock. The patient remained in SVT and, per protocol, the crew increased the energy to 200 joules. Once the shock was delivered, the patient arrested. Following an hour-long resuscitation attempt, the patient was declared dead. When reviewing the code summary from the cardiac monitor, you notice that the paramedic failed to press the sync button and the unit did not deliver a cardioversion synchronized shock as a result. Rather, the second shot disrupted the patient's electrical rhythm and placed him into VFib. Given this discovery, some additional research was conducted, and it was discovered that the monitors used by your service silently leave the sync mode once a synchronized shock is delivered. After a discussion with the paramedic on the call, it became apparent that he was used to another type of monitor on which he had been trained that remained in sync mode until it was toggled off by the user. In an attempt to see if others would make the same mistake, a quick study involving 14 of your paramedics was conducted. After running this study group of paramedics through the same scenario, 50% of them made the same mistake and 71% of those individuals did not even realize an error had occurred. While the results of this impromptu study seem telling, what tests can be done on the results to ensure they are accurate? Are the findings of your study valid and reliable? Is there a possibility that the type of cardiac monitor causes a wider range of variation, or is this a more reliable method of administering synchronized cardioversion? What is the opportunity for management to make a decision on this incident? Is this a provider issue, a system issue, or both? What tool or visual aid should be used to display the results of this test? How best do you communicate the results? In the previous chapter, we discussed data storage and collection. All the data in the world is useless, however, if it cannot be retrieved and, more importantly, statistically analyzed for the purposes of identifying trends, drawing conclusions, or supporting decisions. Within this chapter, we will look at the process of data analysis whereby raw data is prepared and organized so that useful information can be extracted. Such analysis is vital in the decision-making process, especially within the auspices of EMS quality improvement activities. The objective of performing data analysis is to make better and more informed decisions regarding the delivery of EMS. EMS managers must utilize statistical techniques to evaluate data and produce useful information from which data-driven decisions can be made. As a generic assumption, most EMS managers and leaders begin their careers as field providers. With that in mind, the majority of EMS leaders and managers are probably not mathematicians or statisticians by trade. Numbers and data are not always glamorous and exciting, and there are probably a fair number of EMS managers who could think of better things to do than analyze data. So why do we do it? Why is data analysis so important for EMS leaders and managers? Data collection, storage, retrieval, analysis, and summarization takes time and other resources. What is the value? After all, managers make routine decisions every day without performing detailed data analysis. If not already apparent from previous presentations, the value in managing and evaluating data is tremendous, especially in today's day and age where leaders must show data-driven rationale for significant decisions, especially those related to finances and budgeting. Data-driven analysis of outcomes versus the costs associated with providing services can serve as an indication of program usefulness. Data analysis gives insight into healthcare problems, which can have a significant impact on EMS operations. Data analysis can be used to identify training needs based on area EMS problems. Analysis can even impact areas such as workers' compensation, whereby an analysis of data related to personnel injuries may indicate the need for specific training. Additionally, any EMS agency, whether it is tax-supported fire-based, for-profit private, or something in between, is running a business. There are expenses and revenues, personnel to be managed, equipment to be maintained, and other resources to be optimized. Data analysis is essential to determine whether or not the agency is achieving the outcomes expected for the customer, whether the processes used by the agency to produce those outcomes are reliable, and exactly where the agency should invest its resources for personnel training and education. For those not familiar or comfortable with data analysis, the process may seem daunting or overwhelming. As with many other things in EMS, however, following a process is very helpful for both the novice as well as the experienced researcher. When planning for the evaluation of data, the following steps constitute a simple process that helps ensure the end result is the right product. Begin with a plan, then assess, validate, clean, plan again, and finally, do. The first step in data analysis is to be familiar with the data itself. Know the variables involved. Where an electronic database is concerned, this means also knowing the variable names, definitions, and the values collected. Also identify your sources for the information you need. If all of your data comes from a single source, that makes things a little easier. If multiple resources are utilized, however, then you must also plan to compile all of the data within a single database or location. When working with the data, be sure your work does not have the potential to change, overwrite, add to, or delete the original data. Depending on the source of the data, it may be prudent to ensure original files are saved and any work is performed on a copy of that original data. Knowing the type of data with which you will be working is important for selecting the statistical test you will be utilizing on the data. As you go through this planning process, it is not unusual for a researcher to develop more questions related to the research. Be wary of expanding the scope of the research, as too many variables can make it difficult to determine a course of action once the analysis is completed. Keep your research question focused and, if other issues develop, write them down and consider them for possible future research projects. With a research plan in place, it is then time to assess the data you will be using. This is an important step as it drives a second planning process, which will be discussed momentarily. If you remember earlier in the text, data was split into two different categories, qualitative and quantitative. Quantitative data is numbers-based and lends itself very easily to mathematical statistical analysis. Qualitative data, on the other hand, approximates or characterizes, but it does not provide a direct measure. Therefore, qualitative data requires a different analysis process than quantitative data. Within the realm of research, it is also important for conclusions to be based upon an adequate amount of data. If a sample size is small, the results of the research will be less conclusive, less valid. The sample size used has to be large enough to establish both reliability and accuracy. The reason we discuss sample size is because it is commonly not possible to evaluate statistics for an entire population based upon a limited data set. If your EMS agency serves a population of 5,000 people, or 500,000 for that matter, your patient contacts are only a small percentage of that overall population. As a result, your data set does not include the full population, and you must use statistical principles to approximate results for the entire population based upon a sampling of that population, namely, those individuals who have used your services. In determining the sample size, it is necessary to evaluate the overall population to which the research will be applied, the confidence interval to be utilized, and the acceptable margin of error associated with the research. The confidence interval is not derived from the data. Rather, it is chosen by the researcher. It is the degree of uncertainty associated with the sample statistic. If a researcher picks a 95% confidence interval, which is very common for healthcare research, the researcher is stating that he or she believes any values derived from random sampling will fall within the interval estimates 95% of the time. The confidence interval is then combined with a desired margin of error to fully describe the resulting statistics. A margin of error of 5% is common in research, which means the maximum expected difference between the true population parameter and the sample estimate of that parameter is 5% one way or the other. Combined with a 95% confidence interval, the researcher may then say that the results would fall within a 5% margin of error 95% of the time. This recognizes that there will always be outliers who do not necessarily fit within the statistical model, but that is acceptable as the data will help develop systems that are built to accommodate at least the vast majority of foreseeable patients. With the overall population determined, along with a selected confidence interval and margin of error, the researcher can then use a table or perform a calculation to determine the appropriate sample size for the data. For instance, if your agency serves a population of 5,000 people and you want a 5% margin of error with a 95% confidence interval, a sample size of 357 is required. If you want to reduce the margin of error or increase your confidence interval, the sample size will increase. If assistance is needed to determine a sample size, a quick Google search will provide numerous websites that can calculate the value or provide a table with values included. When your data analysis is being performed, the statistical elements of mean and standard deviation are also very important to understand. It is often assumed that statistical research follows what is known as a normal distribution, which is represented graphically by a bell curve. There will be an average or mean value derived from the data, and there will be less instances of outlier data the further one goes from that average. The standard deviation from the mean refers to how widely individuals in a group vary. If individual observations vary greatly from the group mean, the standard deviation is large, and vice versa. Regardless of the height of a bell curve, approximately 68% of all data is contained within one standard deviation of the mean, about 95% is within two standard deviations, and approximately 99.7% of all data is within three standard deviations of the mean. If your data analysis encompasses three standard deviations, it will encompass the vast majority of all possible data points for the target population. Once your assessment of the data is completed, it is now time to validate the data. Validation of data is a process by which the quality of the data is evaluated. Such a quality check typically uses a combination of graphical and numerical techniques to identify any data entry problems, unusual data values, missing data, or wrong characters in a field. As an example, if a review of patient age data includes a 945-year-old patient, it is a good bet that data entry was incorrect. If age is a calculated field within the database, someone may have mistyped the birth year as 1072 instead of 1972. Another example would be a systolic or diastolic blood pressure that contains 4 digits. Such an error would be discovered by something known as a modulus check, which looks for extra numerical digits or fields that should not be valid. Commonly employed graphical tools for validation include both scatter plots and histograms. A scatter plot reveals relationships or associations between two variables. There is a scatter plot example in the textbook. Histograms graphically summarize the distribution of a univariate dataset and does a great job of illustrating the center of the data, the spread of the data, whether the data is skewed, if there are multiple modes in the data, and the presence of any outliers. With data validation completed, the data must then be cleaned, which means not only checking for bad or missing data, as you did during the validation stage, but also adding missing data or correcting data errors where possible. Ensuring your data is accurate is key for delivering valid and useful end-user data. Cleaning your data eliminates errors and redundancy, while also ensuring accuracy, consistency, and completeness. Cleaning data also gives the EMS manager an opportunity to identify issues in the collection of data, which can be used as the foundation for feedback to providers as to how they can improve their data collection and entry. One important facet to consider when cleaning data is that if that data is part of a patient care report, the data should not be changed once the report is finalized without ensuring such changes are documented appropriately. This may mean completing an addendum to the report while leaving the data as is in the original database, which is one of the reasons why it is suggested that any data to be analyzed be exported from the database so it can be cleaned without having to worry about altering vital documentation such as a patient care report. At this point, you should now have a good data set upon which to base your analysis. Now it is time to plan yet again to ensure enough time and resources are allocated to the project and a process is in place for everyone to follow. For more complex studies, it may be beneficial to actually use project management software for creating tasks, scheduling work, sequencing events, and creating visual representations of the process and workflow, such as a program evaluation and review tool chart. Within this planning stage, you should consider the time, cost per hour for staff, and supplies that will be needed to complete the research. With everything in place, it is then time to actually complete the analysis. Some research projects are relatively simple, and only simple math is required to develop a cursory interpretation of the data. In other instances, a more in-depth analysis is required, which could necessitate the use of descriptive statistical analysis that helps to either confirm or refute the initial research question. These descriptive statistical analysis tools include counts, sums, measures of center, minimums and maximums, and standard deviations. Depending on the volume and complexity of the data to be evaluated, there is a high likelihood that a thorough statistical analysis will not be possible for a person sitting at a desk with ledger sheets and a calculator. Invariably, even simple statistical analysis of data benefits from the use of computer software designed for that purpose. Some relational databases can perform limited statistical analysis depending on just how robust they were designed to be. Spreadsheet programs like Microsoft Excel or Apple's Numbers can typically perform some simple statistical functions, and there are third-party add-ons for Excel that substantially increase a spreadsheet's statistical processing power. For really heavy processing and better reporting functionality, there are software programs designed specifically for statistical analysis of data. What route works best for your EMS agency often depends upon available funding and the ability to support the type of software program to be used. Various types of analysis can be required for EMS data, and it is often necessary to ensure whatever software program you are using to evaluate quantitative data can calculate the mean and variance within a dataset, perform chi-square tests, and assign correlation coefficients. As mentioned previously, there are two types of data recognized by researchers, qualitative and quantitative. Qualitative data is non-numeric in nature. This type of data requires variables to be classified into categories or groups through a process known as theming and coding. Quantitative data, on the other hand, is strictly numeric. These values can be either discrete, exact, like cardiac arrest survival rates, or analog, continuous, such as waveform capnography. In contrasting qualitative and quantitative data, it is recognized that qualitative analysis can be difficult because the data itself is subjective in nature. Qualitative data is not as concrete as quantitative data that is captured as an absolute static number. Have you ever asked patients to describe their pain? It can be difficult because it is subjective. We may use descriptors like crushing, dull, stabbing, radiating, and so on, but that still incorporates a certain amount of ambiguity, and if you're trying to compare pain across different patients, what one person may describe as dull pain, another may describe as crushing based upon their individual perceptions and perspectives. Within the realm of both qualitative and quantitative data are the concepts of variable and measurement data. Variable data represents something that varies or changes over time. Measurement data, on the other hand, always remains static. The majority of data collected on patient care reports can be considered variable data as it changes from patient to patient, event to event. When previously discussing qualitative data, pain was used as an example of how such data is difficult to quantify because it is based upon subjective impressions. To try and capture qualitative data in a format that can be more easily evaluated, it is common to use scales or rating systems. Continuing with the pain example, this is what we do when patients are asked to rate their pain on a scale of 0 to 5 or 10, or whatever scale is used. When scales are used for quantifying qualitative data, there are a few different types that can be employed. The first type of scale is a nominal scale, also referred to as a categorical scale. This type of scale is a system for classification. It does not place an entity along a continuum. The generated data allows for a simple count based upon the frequency of cases assigned to the various categories. The second type is an ordinal scale, which involves the ranking of items along a continuum. A third type of scale is a continuous rating scale that uses marks at the appropriate position on a continuous line. At one side of the line is one value, and at the other end of the line is another value that is typically very different from the initial or starting value. Such a scale is a form of what is called a semantic differential scale. This is rather common on customer service satisfaction surveys where respondents are provided with a statement and they then indicate if they strongly agree, strongly disagree, or something between the two extremes. In such cases, the scale is said to be itemized as the respondent is provided with a set number of choices or discrete values to select between the two opposite values on the line. A Likert scale is essentially a composite of itemized scales. Often considered to be a summated instrument scale, Likert scales include items that are summed to produce a total score. Given the previous example, a strongly agree may be associated with the value of 2, and a strongly disagree receives a value of -2. When all data is compiled and added, the survey instrument produces a numerical score that can be interpreted for quality improvement activities. A semantic scale is somewhat similar, but it relies extensively on words rather than numbers. If bipolar adjectives are used at the endpoints of the scales, those scales are further identified as semantic differential scales. While somewhat difficult to see on this slide, this is an example of a Likert scale used on a customer service survey for the Upper Pine River Fire Protection District. A copy of this survey is also provided within the textbook. True qualitative data consists of open-ended narrative information, such as an individual's thoughts about the level of customer service received or suggestions for improvement. Because this type of data is narrative in nature, automated processing can be difficult beyond simple evaluation of recognized keywords within the response. As a result, this is data that typically requires a person to physically, manually review it. The first step is called coding, where the evaluator looks for recurring data or themes within the various responses. Once these codes are developed, the researcher then creates categories into which the codes can be organized. The next step, classification, requires that the codes be verified as easily and unambiguously fitting into their defined categories. Using other people to validate that the codes were classified correctly can assist in this step. Once the coding, categorization, and classification are completed, it is then time to compare the categories in terms of word count frequencies to see how often the denoted classifications are raised within the qualitative data. With that information, the researcher then attempts to draw theoretical conclusions about the content in relationship to the research question. Quantitative data, on the other hand, assesses information that can be measured or controlled and requires the researcher to look at patterns of data. In most cases, this means formatting the data into tables or graphs to assist in recognizing those patterns. The steps for analyzing quantitative data require validity checks on the data, conducting descriptive statistical analysis on the data, cross-tabulation and comparison of information within and between target groups, testing the reliability of the data, and determining whether a correlation exists between variables of interest. In conducting a data analysis, the researcher is looking for variations in the data. Such variations can result from either common causes or special causes. Common causes are those causes or data points in the system over time that affect everyone working in the system and affect all outcomes of the system. Special causes are those data points that are outside the normal limits. They are not part of a system and do not affect everyone. They are a result of special circumstances. The existence and identification of special causes is at the core of EMS quality improvement activities. When summarizing data, it is often beneficial to utilize visual means to convey meaning to not only the researcher, but to third parties and interested stakeholders as well. While there are numerous ways to represent statistical data, 6 common chart types commonly emerge as the most popular: pictograms, bar charts, column charts, line charts, pie charts, and dot charts. Ultimately, the most important purpose of using any chart is to indicate conclusions more quickly and clearly than is possible with tables, numbers, or a narrative description. Numbers alone do not always tell a complete or compelling story. Data must be visual to increase the likelihood of garnering the attention of your audience to convey a message or make a point. Along those lines, the right type of chart must also be used to avoid confusion, as different types of data are better represented by different types of charts. Histograms are column charts in which the height of each individual column represents the relative values of a variable. A bar chart allows for a visual comparison of results. Column charts are particularly useful in demonstrating change over time. A line chart is the clearest way for showing fluctuations in a time series. Again, a histogram is a column chart in which the height of the columns indicates the relative numbers or frequencies of values for a variable. This particular example shows call response times in minutes and the number of calls that were responded to within a given period of time. Just a brief glance at this type of chart conveys to the viewer that the majority of responses have response times that range between 2 and 8 minutes. Longer response times are obviously undesirable, and this chart shows that, while there are some longer response times for this service, they appear to be the exception rather than the rule. This is another histogram related to the number of civilian casualties due to fire or smoke based on age. As a note, the histogram itself uses the word casualties, yet the citation states injuries. This could be confusing to a reader as the two terms describe different outcomes. When producing your charts, it is important to make sure your terminology is consistent between any labels and headings provided. Another type of bar chart is a Pareto chart, whereby vertical bars are ordered in decreasing order of relative frequency from left to right. In such a graph, the element with the greatest frequency tends to jump out at the person viewing the chart, given its predominant placement on the left-hand side of the chart. In this particular example, it would appear as though there were 50 occurrences, encompassing 54% of all chest pain cases, where aspirin was not given in violation of service protocols. This is an example of a line chart that shows the call volume for a service over a 24-hour period. As line charts are excellent for conveying increases, decreases, and fluctuations in a time series, it is a perfect choice for this particular data set. A clear pattern emerges in that call volume is at its lowest during the early morning hours from midnight to about 6 or 7 a.m. Volume tends to peak around 4 to 6 in the evening. Additional chart types include pie charts, which are effective at showing how each component contributes to a whole, dot charts or scatter diagrams that emphasize the relationship between two variables, and a pictogram, which provides a great way of depicting data by geographical areas. Here are some examples of different pie charts. Again, pie charts are great for showing how each component contributes to a whole. Thus, pie charts are good for displaying data that can be denoted in percentages. Looking at the trauma statistics provided, it is relatively easy to see at a glance that males have higher trauma incident rates than females. The largest age groups suffering from traumatic events are the 65 and older category, and the race most impacted by traumatic injuries is white. To really complete the picture, it might be helpful to also have some demographic data included. For instance, if the community had a low population of whites in comparison to other races, that might make one wonder why the particular racial group is experiencing traumas at an elevated rate. On the other hand, if the community served is 95% white, those same numbers take on a different meaning. Dot charts or scatter diagrams are useful for evaluating the relationship between two different variables. In this example, the dot chart plots first attempt IV success rates against years of provider experience. Upon a quick glance, it would appear that more experienced providers have better success rates than newer providers. To confirm such a relationship, statistical software can calculate a correlation value, or R value, where -1 is a strong negative correlation, 0 is no correlation, and +1 is a strong correlation. One thing to be wary of when using such data is that just because two variables are correlated does not necessarily mean the relationship is causal. For instance, the chart gives the impression that more years of experience results in better IV success rates. Would your impression of the data change if you found out the service's most experienced providers commonly receive assignments at stations where they have lower frequency of critical calls, and those with little seniority spend a lot of time responding to a large nursing home complex that cares for severely sick people? What if the people with more experience performed only a few IVs during the sampling period? How reliable would that data be? Such questions are not addressed in the chart itself, yet they are very important in being able to interpret the results. While this presentation is by no means intended to replace a statistics course, it is important to have at least some familiarity with statistical principles when analyzing EMS data. For that reason, we will delve a little further into some basic statistical concepts. Collected data can be distributed across the dataset in numerous ways. Two of the most common or important distributions in analyzing EMS data are cumulative frequency and cumulative percentage frequency distributions. A cumulative frequency distribution is the number of data points that are less than or equal to a given value. The textbook contains a good example of this by denoting the number of runs in which the response time was within a particular range. For example, 129 runs had response times of less than 1 minute, 206 runs had response times from 1 minute to 2 minutes, 759 runs had response times of 2 to 3 minutes, and so on. The cumulative part essentially adds up the numbers to encompass all thresholds at or below the last category value. Using the same data, there were a total of 335 runs with a response time of 2 minutes or less, 129 that were less than 1 minute plus 206 that were from 1 to 2 minutes equals 335. There were 1,094 runs with response times of 3 minutes or less, 759 plus 206 plus 129 equals 1,094. This running total, the cumulative frequency, is then calculated until there is no more data to include. A cumulative percentage frequency simply converts these cumulative frequency numbers into a cumulative percentage. Within the textbook's example, there were a total of 5,394 runs evaluated. 2.4% of these runs had response times of 1 minute or less, 129 divided by the total runs of 5,394. 6.2% of the runs had response times of 2 minutes or less, 335 divided by 5,394. 20.3% of the runs had response times of 3 minutes or less, 1,094 divided by 5,394, and so on until 100% of all runs were accounted for. Central tendency is a method that provides a single summary figure that describes the central location of an entire distribution. There are a few ways to calculate a central tendency, and the number generated may not always be the same for the particular data set. The three most common measures of central tendency are the mode, median, and the mean. The mode is the number that appears most often in the distribution. The median is the middle value in the data set when the values are listed from smallest to largest. If there is an even number of values, then the median is the mean or average of the two middle values. The mean itself is the calculated average of the entire data set. Take the data set of the following 9 numbers: 1, 4, 4, 4, 5, 6, 7, 7, 8. The mode is the number that appears most often, 4. The median is the middle value in the data set, 5. The average is calculated by adding the values and dividing by the number of values in the series, 1 plus 4 plus 4 plus 4 plus 5 plus 6 plus 7 plus 7 plus 8 divided by 9 equals approximately 5. 5.1 if a decimal is used, but because the numbers were simple integers, the mean integer value for the series would be 5. As far as qualitative data is concerned, the mode is really the only central tendency measure that can be used. Beyond qualitative analysis, the mode is typically not a very good statistical value, as it is commonly considered to be an unstable measure of central tendency. Equal-sized samples taken from the same distribution will commonly have a different mode. There can even be more than one mode in a distribution, which can be confusing if that was the only measure of central tendency used on a dataset that essentially has more than one peak value. One might think that the mean is the best measure of central tendency, and in most cases, that is probably correct. One problem with using a mean in all cases, however, is that the mean can be heavily influenced by outlying or extreme values in a distribution. Consider our previous 9-number series with no value exceeding 8 and a mean value of 5. If the last value was 16 instead of 8, however, the mean would have been significantly affected, resulting in a calculated value of 6 instead of 5, despite the mode and median remaining the same at 4 and 5 respectively. To provide a better picture of the data, the calculation of central tendency is commonly combined with the measure of dispersion, which provides a summary of the variability of the values within the dataset. One such measure of dispersion is the range, which simply calculates the difference between the highest and lowest values in the dataset. In our previous example, the range was 7, the highest value of 8 minus the lowest value of 1. Variance is another measure of variability within a distribution of data. Variance is calculated by squaring the differences between each number and the mean, adding those numbers, and then dividing the resultant sum of the squares by the number of values in the set. If the variance is small compared to the mean, the values in the data set are obviously close to the mean. If the variance is large compared to the mean, however, the values within the data set are further away from the mean. For what it's worth, the values in our previous example have a variance of 4.6. We already talked about standard deviation briefly earlier in the module. Standard deviation is another measure of dispersion. The calculation for standard deviation is simply the square root of the calculated variance. In our previous example, the square root of 4.6 is approximately 2.1. Thus, the standard deviation for our 9-digit data set is 2.1. While the math itself is not too complicated, as the number of values in the data set increase, it becomes less and less prudent to manually calculate these statistical values. This is where computerized software becomes invaluable. Additionally, it is important to keep in mind the difference between calculating statistics for an entire population versus a sampling from the population. If you are calculating a variance or standard deviation for a sampling versus an entire population, the math is just a little bit different. The denominator in the variance calculation is decreased by a value of 1. Statisticians usually assume that any given set of data values will be distributed normally. If that is indeed the case, the mode, median, and mean of the data set are all the same. Such a normal distribution also means that half the values are above the mean, half the values are below the mean, 68% of all values are within one standard deviation of the mean, 95% of all values are within 2 standard deviations from the mean, and 99.7% of all values are within 3 standard deviations from the mean. When looking at measures of dispersion, the range can be an ideal value when precision is not important. Because the range is not sensitive to the total condition of the distribution and looks only at the 2 outermost values, its use is essentially limited to descriptive statistics. Variance and standard deviation are typically better measures of dispersion, as they are both sensitive to the exact position of each value in a distribution. One issue with the statistical analysis of data is that it is common to assume a normal distribution, which may not always be the case. It is not uncommon for the distribution in data sets to be skewed one way or the other, with more values, or larger or smaller outlier values, toward one side or the other of the distribution. Luckily, all is not lost, however, as the central limit theorem states that the sampling distribution of means increasingly approximates a normal distribution as the sample size increases. Therefore, even if the distribution of a dataset does not follow a perfect bell curve, it is still possible to conduct a statistical analysis of the data based upon the assumption of a normal distribution, so long as enough data points are available. As already mentioned, a lot of the data collected within EMS is qualitative, not quantitative, in nature. This means that the data does not lend itself to traditional statistical evaluation techniques such as determining a mean, median, and standard deviation. To facilitate the analysis of such data, tables are often used that indicate the number of times a specific qualitative category is documented. Such tables then lend themselves to nonparametric statistical analysis, which make it possible to analyze categorical data. Nonparametric statistical tests make no assumptions about the probability distributions of the values being assessed. One of the most popular nonparametric statistical tests for qualitative EMS data is the chi-square test that determines whether the percentage distribution from a table differs significantly from a distribution of hypothetical or expected percentages. Another important statistical measure that is often used in the analysis of EMS data is that of correlation. Correlation in data refers to the statistical measure that indicates the degree to which one variable changes with another variable. An example provided previously in this module was the scatter chart that included years of EMS provider experience versus first attempt IV success rates. As a provider's years of experience increased, it appeared as though the success rate also increased. This would be a positive correlation. In data sets where a correlation exists between 2 variables, it is easier to make predictions as to how changes in one variable should then impact the second variable. The stronger the correlation, the more accurate predicted values will be. When discussing correlations, keep in mind that a linear relationship between the 2 variables is assumed. That is, the relationship is best described or represented by a straight line. As it is possible to have correlations that are nonlinear in nature, such relationships are not easily described by a simple linear correlation model. Additionally, as mentioned earlier in this module, correlation does not imply causation. When calculated, a correlation coefficient is produced to indicate the strength of association between the two variables. Correlation coefficients vary from a -1 to a +1. A value of -1 is a perfect negative correlation, which means that one variable goes up at the same rate as the other variable goes down. The relationship is inverse. Essentially, all points plotted on the scatter chart form a decreasing line. A value of +1 is a perfect positive correlation, which means that one variable goes up or down at the same rate as the other variable. Given a perfect correlation value of 1, all the points on the scatter chart form a line with a positive slope. Between those two values is the correlation coefficient of 0, which means there is absolutely no statistical relationship between the two variables. They are completely independent of each other. Perfect correlations, either positive or negative, are exceptionally rare. Thus, the strength of a correlation exists on a sliding scale. A correlation coefficient value of 0.7 indicates a strong positive linear relationship between the variables. A -0.5 would be indicative of a moderate negative linear relationship. A correlation coefficient of 0.3 would be considered a weak positive correlation. Remember, the sign, either negative or positive, indicates direction, not magnitude. Magnitude is indicated by the number itself, with the stronger correlations being toward the ends of the spectrum from -1 to +1. The correlation coefficients themselves are also not mathematically related to each other. They do not represent a percentage value or a relative strength. 0.6 is not twice as strong as 0.3, for instance. If one wants to make a direct comparison of correlations, the correlation coefficient must be converted to a coefficient of determination. This is done by squaring the correlation coefficient value and then multiplying by 100. A correlation coefficient of 0.5 is indicative of a moderate to strong relationship, yet it is only a quarter as strong as a perfect 1.0 correlation. Using this calculation, it is also evident that successive correlation coefficient values do not represent equal differences in degree of relationship. The difference between 0.4 and 0.5 is not the same as 0.9 and 1.0. There is a table provided in the textbook that includes the coefficient of determination for common correlation coefficient values. Feel free to review it to further explore the differences in magnitude between correlation coefficients. Please be aware that there are actually different types of correlations used in research. The Pearson product movement correlation coefficient is commonly used in EMS research for continuous quantitative data. Rank order correlation is useful for categorizing data by ranking. Biserial correlation is used for data in which one variable is continuous and quantitative, and the other would be if not for the fact it has been reduced to just two categories. Point biserial is used when the second variable is qualitative and divided into two branches that could not be expressed as continuous and quantitative. Again, most EMS providers, managers, and leaders are not trained mathematicians or statisticians. If the data to be evaluated is complex, it may be beneficial for the EMS agency to work with academia to perform a proper statistical analysis of its data. In revisiting our earlier scenario, an analysis of variance and a quantitative step-by-step process can be conducted to determine if the failure in procedures is significant or a random error within the normal standard deviation of events related to ventricular tachycardia. We know the findings are valid and reliable because this resulted in a sentinel event. Therefore, any similar event, even if conducted in a laboratory or controlled environment, is significant. The Pearson product movement correlation coefficient could determine if one cardiac monitor is more likely to propagate the error than another, given that all paramedics are familiar or trained on each monitor. What is more important is if the training is correlated to the right type of cardiac monitor that the paramedics are most likely to use. As far as this data is concerned, histograms, pie charts, or two-dimensional bar charts should be more than adequate to display the results graphically. To reiterate, data is not useful unless it can be analyzed to develop conclusions and make decisions. The distribution of the data in question is important in any analysis of that data. Any conclusions drawn on the data must be tested to ensure they are based on accurate, reliable, and significant data. Once the analysis is performed, the data must be accurately displayed graphically or in a tabular format to assist others in understanding the results.